So finally I'm going to be in one of the videos. I wish it had not come to this, but I needed more room because what we're learning in 11.2 are 6 more rules for differentiation, and that's added on top to all of our other ones. So what we're going to be really kind of considering now is not only do we have to adopt these, but we're also going to have to be mixing them in with our old rules as we're working through some of these differentiation problems. Alright, so your goals for this, or your objectives for this 11.2, are really to be learning these. Okay, you are going to have to memorize these 6 right here. There's more to come, but for now, those are the ones that I want you to be working on. So I did kind of something that's clever. On the backs of these, I have all of the differentiation rules. So sine of u is the easiest one if we were deriving this function. And keep in mind, this is a function within a function. We're deriving with respect to x. So right here, what we're saying is when we take sine of u, we don't know what u is equal to. So when we're looking at this, we're going to not only be able to derive sine, which is just cosine of u, we also have to multiply it by the inner function's derivative. So we're going to take this and break this down in an example. Alright, so this is what I do have up here. I'm going to let u equal 2 times x. And so what I'm going to be looking at here is sine of a composition function where we're taking sine of some sort of inner function. So when we're looking at this is its own function in its own right, and then we're putting it through sine. So I'm going to match it up with this rule, because that's what I'm doing here, and I'm going to be saying that if I wanted to derive this, the derivative of sine of 2x is going to be equal to cosine, that's this rule right here, cosine of 2x. Okay, so I've derived sine, but then you have to go ahead and take this times the inner function's derivative. So if you want to, you can go ahead and derive u with respect to x. What we're just going to get is 2. Okay, so all in all, the best way to write this is 2 times cosine of 2x. Okay, so that's kind of just a breakdown of how this works. Keep in mind that if I were driving sine of x with respect to x, so had this been a sine of x here, it would have just been cosine of x, okay, because you wouldn't have any inner function to derive. So ultimately, when you derive sine, it becomes cosine. And I have those for each one of these. So the derivative of cosine is almost as easy as sine. It's almost as easy as just switching it over to sine, except for you have to negate it. If you derive tangent, remember when we were looking at the Pythagorean theorems, tangent is really related to secant in the Pythagorean theorem. It's also related to secant squared in this differentiation process. Alright, if you're driving cosecant, they get a little bit tricky. You're going to negate cosecant and then also attach it to that cotangent. And again, in the Pythagorean identities, they were also related there too. But then don't forget to multiply by the inner function's derivative. Secant, once again related to tangent, you're going to keep secant. Multiply by tangent, inner function's derivative. And cotangent, negative cosecant squared. Okay, so those you're going to need to write. I would probably write that at the beginning of your assignment. That way you have it for your use. That way you don't have to flip back through those pages. But all of those rules are in your book in this 11.2. So we're going to now work through examples. So now I'm going to start looking through our problems, and we're going to work through some as examples. So now we're going to start to look through some of our problems and work through these examples and start bringing this all together. So I'm going to start off with a basic one. We're just going to do number 1. And they give us f of x Okay, so in solving this problem, what we need to realize is I have a few things going on here. So I have two functions being added together, and what I'm trying to find is f prime. So you could go ahead and write dx on this side, dx on this side, saying that we're going to differentiate both sides. One notation, of course, is this f prime. So I'm going to have to do this thing where I have to differentiate this whole entire side. So here's the thing. I have two functions being added together. Remember this sum and difference rule? This one's the nicest of all of them because if you're adding terms together and you want to differentiate them, what you can just do is break them up piece by piece. That's the only one that you can actually do this for. You can rewrite it as the derivative of u plus or minus the derivative of v. You can't do that for multiplication. We have the product rule for that. You can't do that for something with division because we have the low d high minus high d low all over low squared for that. This one's the most convenient one to work with. So adding or subtracting pieces, you can go ahead and differentiate piece by piece. So I'm going to do that. The next one that I'm going to use is I have these constants on the outside, these scalar multiples. So we have our good old scalar multiple rule. So we're going to be using this now. And what that says is you can just go ahead and pull out that constant and derive the function that's involved. So here I'm going to pull out that 2. And keep in mind I am doing this very much piece by piece. But this is what we're going to be getting it down to. Plus 3, and then d. So now, at this point, what I can say is I'm using this rule right here. The derivative of sine, you can go ahead and write as 2 times, and then here it's just cosine of x. Okay, no inner function to derive, so we just have to derive this outer function, which is, or we just have to derive sine, which is equal to cosine of x. And then plus, ooh, that's nice, 3 times, if you derived cosine of x with respect to x, it's just going to be negative sine. That. Negative sine of x. So best way to write this in the end is going to be 2 cosine of x minus 3 sine of x. That's it. Alright, so number 28 looks like this, and the directions that they gave you were to find the slope of the tangent line at the origin, so at the point 0, 0. So when we're doing this, what you have to keep in mind is that the tangent is the rate of change, which is going to be slope. But that's what this differentiation is all about. Differentiation, finding the derivative, is the general equation that's going to give you the slopes of all the tangent lines on a certain function. So they actually have this graphed here, which we're very capable of graphing. And they kind of give you the image of it. So, I mean, it is a sine curve, and this is a really rough sketch, but it's doing something like this, okay? And what we're trying to find out is what is the slope of that line at the point 0, 0. What is the slope of the line that touches this graph just one time through that curve? So in order to do that, we are going to have to derive, oops, I put these backwards, but, whoops, so I want this one. We're trying to derive, it's actually exactly this, just the basic sine of another function. So, I am going to be, I'll put it right there. What we have is y prime. If I wanted to find the derivative of this function, it's going to be cosine of that inner function left alone times the inner function's derivative, which is 3. Okay. So the best way to write this is y prime is equal to 3 times cosine of 3x. Here's the deal though, this is the general equation. It would provide you with the slope of every single one of these tangent lines on this graph. So you could go ahead and calculate if this were pi, for example. Let's go ahead and, if this were pi, for example, right here, and I wanted to figure out what was the slope at pi, x equals pi. Well, you could plug in pi into this equation and it would give you that exact slope of that line. If I wanted to figure out what was the slope at, let's say, pi halves, so the slope right here at pi halves, you could ask yourself, all right, let's plug in pi halves into this equation and it's going to get you the slope of that particular tangent line. But what we're really interested in right here is the point 0, 0. So you just take that x value, plug it in. This maybe is the better way to write it. Okay, so 3 times cosine, 3 times 0. What this is going to amount to is 3 times cosine of just 0. If you look at your unit circle, what is cosine of 0? Well, it's just 1, it's that x value, so it's going to be 3 times 1. So, 3. Okay, that's what we're looking for there.